Good evening, welcome to BrisScience. As you've probably noticed, I am not the charming, debonair Joel here this evening. My name's Dominic Jarvis, I'm one of the organisers here. Joel has decided to be gallivanting across the world this evening. I think he's in Spain currently, so we'll see him with an accent and a sombrero next month. But I'd like to welcome you all to BrisScience this evening and kick off tonight by acknowledging the traditional owners of the lands on which we're gathering here this evening. Please put your phones on silent, but we'd love it if you could keep them out and scan our code, which was just there. I think we'll get it back in a second. If you've got any curly questions for Professor Bowen this evening, that'd be great. Anything about quantum, anything about medicine. If you want to show him your rash, please do that after the presentation. So remember, there's also finger food served after tonight, so please stick around, and for any particularly curly questions, you can go straight to Warwick then. So tonight we're going to be taking a quantum leap into quantum biotechnology and what it might hold for our future. Quantum technologies like quantum computers and sensors allow us to see things that are otherwise invisible and to perform computations that would otherwise be impossible. Quantum technologies could promise the next health revolution. So our guest tonight, Professor Warwick Bowen, works to develop new quantum and precision measurement technologies. He works with industry to apply them in fields ranging from biomedicine to aerospace, resources and energy. He's director of the Australian Centre of Excellence in Quantum Biotechnology and a fellow of the Australian Institute of Physics. He's made important contributions to the application of quantum light in biological microscopy and to the unlabelled detection of single proteins. Please welcome to the stage Professor Warwick Bowen.
Well, it's really my pleasure to be here to speak to all of you today, and it's great to see so many people out at BrisScience. Hopefully we'll give you a bit of a show. Thank you, Dom, for your kind introduction and for making this happen, and for everyone else also who's behind the scenes making BrisScience such a great thing. As Dom says, I'm the director of a new centre in Australia. It's the first national centre in the world that aims to bring quantum technologies into the life sciences, into health, into medicine, into energy, into agriculture. And it's really great to be here to tell you a bit about why quantum technologies could really change society in the next few years. I wanted to start by just saying, isn't it amazing the world we live in now? We often forget that we're so lucky that so much technological progress has been happening and that we're able to do so many things now that we weren't able to do. It's really an incredible time to live. But we have incredible challenges too, from how we sustain agricultural production to keep society fed, to how we address the growing resistance of diseases such as bacteria to treatments, to the fact that our populations are becoming increasingly aged. How do we maintain quality of life as we get older and live longer? To climate change, one of the biggest challenges we face as a society. Today I want to tell you that quantum technologies, they won't solve all of these problems, but they have a major role to play in helping to address these problems. Quantum started 100 years ago, a couple of months from now, this year. And it started when a bunch of quantum physicists got really puzzled at about a few little things that didn't quite work at the scale of atoms and electrons and photons. And that resulted in a new theory, which was really forced upon us. No one wanted to believe this theory called quantum mechanics, but it was the only way we could explain what we were observing. And as Bohr, who's this guy here, observed at the time, if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. It completely changed our understanding of physics. And if that's all it was, then that would be really interesting for physicists like me. But it also changed society. Our understanding of the quantum nature of materials led to semiconductors, which led to transistors, which led to computers, which are, of course, completely transformational to how we live now. Our understanding of light and its quantum properties led to lasers and all modern communication systems. And our understanding of the quantum nature of atoms led to global positioning and many other applications. So this is what we call quantum 1.0. Just understanding quantum mechanics, being able to write down the theory, changed our ability to build technologies. In the health space, it enables many of the medical imaging systems that you will use in your lives. The quantum properties of atoms, this is the spin of the nucleus of your atoms, enables magnetic resonance imaging. Quantum entangled gamma rays, which are a type of radiation, are what enable positron emission tomography for cancer treatment. And very precise quantum magnetic sensors enable the best tools we have to image your thoughts, to image currents in our brain. These are just some examples. What I think is particularly profound about quantum mechanics is it tells us how molecules work, and that means it tells us about how all life works at some fundamental level, as well as, of course, materials, such as semiconductors. Before quantum mechanics, our understanding of the atom was that there was a positively charged nucleus with negatively charged electrons orbiting it. But physicists knew at the time that this model couldn't be right. And they knew that because of the same physics that you use to communicate every day on your mobile phone. If you look into your phone, there's these little elements, which are called antennae, and those elements basically just wiggle electrons around, and when those electrons wiggle, they generate an electromagnetic field. That is the field that communicates from your phone to an antenna, to a cell site. Okay, so that's fine. Why is this relevant to atoms? Well, atoms wiggle electrons around too, at least based on models before quantum mechanics. These electrons are moving. So they should radiate electromagnetic fields. They should lose energy, and therefore how can they be stable? We didn't know how to explain that until quantum mechanics came along, and quantum mechanics told us you have this all wrong. Electrons do not orbit the nucleus. They exist in clouds spread out across the whole nucleus. And those clouds can have different sorts of shapes. They're called orbitals. Excuse me. And then, if we understand electrons as existing in clouds, we can understand chemistry. So here I'm showing you some chemical reaction where two constituents are moving around and their electron clouds are changing as they do that. So now we can start to really understand how molecules interact with other molecules, which is the fundamental of all matter, really. So that's been incredibly transformational. We can now model how drugs interact with molecules in your body, with proteins in your body. We can design materials based on quantum mechanics. There are many things we can do. But quantum mechanics tells us something else that's very, very deeply profound. It tells us that molecules are far, far, far more complex than we'd previously thought they were. And I want to go through why that is with you. It comes from two properties of quantum mechanics. The first is called the superposition principle. And this is that quantum particles do not exist precisely in a single location. That is to say, if I look at my atomic orbital, is the electron here or is it here? Well, it's actually, in some sense, in both places and in all places in that orbital at the same time. It does not exist in one place at one time. So that's called superposition. It's in a superposition at different places. The second property is something called entanglement. This is a property of quantum particles that says they can be very deeply correlated to each other. So if you want to think about that, you could have a system where if one electron was here, even though it actually exists spread out, the other electron in this other atom might be here, right? Okay, so why am I telling you this? These two properties are the most fundamental properties of quantum mechanics. And now let's do a little thought experiment. This is the only maths in the presentation, so I apologize. I hope we get through it. Let's say I have a single electron, and it can exist in m different locations, right? Some number of locations. Then, if I have a molecule and it has n electrons, so not just one, then the first electron can exist in m locations. For every one of those locations, the second electron can exist in m locations. So if I had 2, I'd have m squared locations. But if I have n, it turns out that there are m to the power of n total locations, that electron, possible configurations of all of those electrons. Okay, fine. So let's imagine just 10 electrons. So that's, a typical number of electrons that one atom might have. And let's imagine that they're in a 10 by 10 by 10 cube. There are 1,000 different positions that each electron can sit on. And if I calculate this number, I get, this is a very small problem, right? But if I calculate that, because there are 10 to the 20 atoms in this little bit of space, right? I get 10 to the 30. And 10 to the 30 is a number that's so large, it was very difficult for me to figure out how to convey to you how large it was. So this is what I came up with. Imagine we're on the Earth here, and I stack atoms on top of each other into a tower, and I stack 10 to the 30 atoms in that tower, then that tower will reach halfway to the middle of the galaxy, right? So it's an insane amount of atoms. So, okay, why is this relevant? It's relevant because quantum mechanics, these two properties, superposition and entanglement, require, if I want to understand the dynamics of a molecule, for me to follow all 10 to the 30 of those numbers, right? That is a lot of numbers. In fact, if you ask how many numbers can all existing computers on Earth contain, you'd need 10 million Earths to be able to do that one, to calculate that one thing, that one simple problem. Right. Now, molecules are typically much bigger. So 10 to the 30 is actually a very small number as far as molecules are concerned. So this is in some sense exciting. What it tells you is that nature may be able to do all sorts of things. It's telling you there's this richness that's almost infinite in nature, right? But it also tells us something that for a physicist is less satisfying, and that is that maybe we can never properly understand nature. Maybe there's just no way that we're ever going to be able to do computations that tell us how nature works at its most basic level. So this is a consequence of quantum mechanics. And this very question turns out to be the fundamental start of the field of quantum technologies some 40 years ago. And it came from an observation from a very famous quantum physicist, Richard Feynman. He noticed, he said this, he said, nature isn't classical. And he's thinking it's really complicated because of quantum mechanics. If you want to simulate it, you'd better make that simulation quantum mechanical. He's essentially asking, can we use the same complexity that exists in nature because of quantum mechanics to model nature? And that observation led to 40 years or so of effort from physicists in developing quantum technologies. What we've been trying to do is go from understanding quantum physics as it exists in nature to engineering quantum technologies that can take advantage of the quantum properties of matter. And that has been a remarkably successful endeavor around the whole world, which has now led to the belief that quantum technologies could result in economic impact at the level of $1 trillion within a decade or so of now. And what I think is really nice about this is that a great deal of that impact is in the stuff that matters to people. It's in health. It's in the life sciences and agriculture. It's in clean energy. Here are some examples of application areas in that space. QBIC, the ARC Center of Excellence in Quantum Biotechnology, was established precisely to drive these sorts of applications of quantum technologies. What we do is we take quantum computers and we take and develop quantum sensing and imaging systems, and we apply them into health, energy, agriculture, and pharmaceuticals. The basic premise is this. It's that the body is an extremely complex organism with complexity from single molecule level to cells to the to organs in the whole body. And quantum technologies can allow us to understand all of these different dimensions with better precision and detail than is otherwise possible. I want to tell you a little about quantum computing, and then I'll tell you about sensing and imaging. The principle of quantum computing is to use quantum superposition and quantum entanglement to do computation. And the key difference is in a conventional computer, which quantum physicists call a classical computer, you have zeros and ones that carry information. In a quantum computer, I have a qubit rather than a bit. And that qubit, I said there was only one equation. I lied. That qubit can exist in a superposition. This alpha and beta is some probability amplitude that the bit is 0 or 1. So it can exist in both a 0 and a 1 simultaneously. That's quantum superposition. At the same time, 2 qubits or more qubits than that can be entangled. They can be quantum correlated to each other. And it turns out exactly the same exponential complexity that we find when we try to model molecules comes out in a quantum computer. The power of a quantum computer goes as 2 to the number of qubits. So remember, 10 to the 30 was a big number. If I had, in a regular computer, I have trillions of bits. If I had 100 bits here, I'd have 2 to the power of 100. That's an extremely big number. So I don't need an enormous quantum computer to in some sense, have a deeply powerful way of solving computational problems. Okay, so that's how a quantum computer, where it derives its power from. Now, if you look around the world, you'll find people developing all sorts of different types of quantum computer. This is not an exhaustive list, but quantum computers based on conduction in aluminium when you cool it down to low temperatures, called superconductivity. Computers based on photons of light. Computers based on single ions, so atoms, but with one extra or missing electron. Atoms trapped in lasers. And quantum computers based on silicon chips, like our regular silicon chips, but with some fancy things going on. And there are many companies building these computers. This is a representative list. It's not exclusive. There are billions of dollars being invested to make these computers work and make them be useful. And a lot of that's happening in Australia. So we have We have a bunch of quantum computing companies that have started up here. Here are two examples. And we have major efforts from other large quantum computing companies such as PsiQuantum, Google, and IBM. It would be remiss of me if I didn't mention that PsiQuantum, the world's largest photonic quantum computing company, will be building their first utility scale, or in other words, a useful quantum computer here in Brisbane, quite close to where we are now. So it's very exciting times for us in the quantum industry. Okay, so that's the exciting part. The reality check is that no quantum computer can do anything useful yet. This is a plot of the error rates in quantum computers versus the number of bits. And we're currently around here, and we need to get to here. Right? We're not there yet. We can't do anything useful. But because quantum computers, the power grows exponentially with the number of bits. You add one bit, you make a very big difference in the capability of the computer. And indeed, if you're familiar with conventional computers, what has been remarkable is that every year, the number of transistors in a regular computer grows by a factor of 10. And that's happened since 1970. This is called Moore's Law. This is why you can fit a whole powerful computer in your phone now. And the same thing is happening with quantum computers. This is an example of the same exponential scaling in the power of a quantum computer. You could ask me afterwards what quantum volume means, but it's essentially something like the size of the computer with time. And actually here we're showing an increase of a factor of 16 in 1 year. So there's dramatic progress towards useful quantum computers, and it's likely we will get there with one or more types of quantum computer in the next 5 to 10 years. What will we do once we have useful quantum computers? Well, I'm going to tell you about 3 big problems. One, the first one, you will recognize what these things are. That's a COVID virus. Currently, when pharmaceutical companies develop vaccines, it typically takes them something like $1 billion in 10 years, more than 10 years, to get one vaccine from an idea to market. And a big part of that, there are many aspects, but a big part of that is they're not good at picking winners. They have many molecules they'll pick, and then most of them don't get all the way to a useful, don't end up working out. Quantum computing could allow us to pick winners better because it allows us to model molecules more precisely. Similarly, dementia is the leading cause of death of Australian women and the 3rd leading cause of death of Australian men. I think it just overtook cardiovascular disease as the leading cause of death of Australians. And it is thought to be due to misfolding of proteins in the brain. But we do not understand its microscopic origins. Quantum computing could help us to understand and potentially create treatments for this very severe and distressing disease. Here I'm showing you some plants. Maybe it's not obvious why I should show you plants. The reason is this. Agricultural productivity is critical to humanity, and we rely on ammonia-based fertilizers. 1% of world energy is used to make these, and 4% of world methane. They use a 100-year-old process. But plants, legumes, inside their root system, they have these little enzymes that can make ammonia at room temperature and ambient pressures. In our processes, we need to use very high pressures and very high temperatures, and that makes them energy expansive. So if we could understand how plants do this, we could transform the energy cost and methane cost of ammonia production. It's just one example of somewhere that quantum computing can potentially help us to move towards net zero while also addressing a big societal challenge. Okay, that's the quantum computing story. Let's talk about sensing and imaging. Microscopes have been around for a while, since the 1500s. This was one of the first microscopes ever made, designed by Robert Hooke. As soon as they were developed, we started to learn things that we didn't previously know about nature. We learnt that there were things called cells, that were building blocks of life. In the 200 years that followed, our whole understanding of disease was rewritten. Dom was asking me about your rashes. Please don't do that. But some rashes are caused by mites. We didn't know that until people observed them with microscopes. The malaria parasite was discovered with microscopes. And this history has just continued year after year, decade after decade, century after century. So now we have the most amazing tools to see the body, from whole brain imaging systems such as MRI, to microscopy that can tell you about living cells in unprecedented detail, to even microscopes that can observe the structure of single proteins in your cell, or enzymes, at atomic precision. This is a big part of the reason why our life expectancy has gone up, and why cancer deaths are going down, and why our health system is so effective. But we're so far away from where we would need to be if we wanted to understand all of life. There are more neurons in the brain than stars in the universe, I believe. I'm just remembering that off the top of my head. I may have it wrong, but it's something like that. And we don't see them at all here. We just see general patterns. They're invisible to that imaging system. Cells have millions of enzymes and proteins and things doing work which are completely invisible to these microscopes. And while we can see single atoms in these microscopes that can image single proteins, they're frozen out. So you can't see the motion of those proteins, and life is ultimately motion. If you stop, you're dead, right? So there's a lot we need to improve. And quantum technologies are, and will continue to, help with that. This is an example. This obviously is not for medical imaging. This is one of only a few observatories in the world that's able to measure mass in the universe. It gives us eyes on mass in the universe. The way it works is it's kilometers long, and it has a laser beam propagating down these two arms, and it measures the difference in the lengths of the arms in order to measure ripples in space-time in the fabric of the universe due to black holes colliding and other macroscopic events. In order to do that, you need to be able to measure distances like at the length of a kilometer with a precision way beneath the width of an atom. So crazy precise precision. So in our center and around the world, we are taking these sorts of technologies, miniaturizing them to microscope scale and chip scale, and applying them to observe biology with the same unprecedented precision. We build quantum sensors based on clouds of atoms in vacuum chambers that have completely changed our ability to measure time and our ability to measure magnetic fields, such as the fields from our brain. And we build quantum sensors where you take a little chip of diamond, remove one atom and replace it with a different atom, and use that as a quantum sensor for very small things such as proteins, and even for imaging whole cells and neural networks, the brain. I'm not actually sure how much time I've got left, to be honest, but I didn't quite figure out where the clock was. But I want to say, I've got 15 minutes left. Okay, good. All right, I've gone a bit faster than I'd planned, which means I'll have plenty of time for questions, which is good. But I wanted to finish with one example, and I think it's a really significant example. This example is magnetic encephalography, or MEG. So MEG is the best tool we have to see currents, neural currents deep in the brain. So, when you think, that involves charge motions. Those charge motions generate magnetic fields, and MEG measures those magnetic fields to literally observe your thoughts. It's a really important technology. If you have epilepsy, for example, and you're going to have surgical treatment, you will get an you get an MEG scan to tell where the epilepsy is and how extensive it is, to guide the surgeon in knowing how much of your brain they need to take out to treat your disease. It turns out that MEG is a quantum technology. So inside this sort of big helmet, that's actually an enormous thing, you're only seeing the bottom of it, there are these little devices that are called squid magnetometers, not squid like the fish, squid as in superconducting quantum interference device magnetometers. These are essentially the most precise detectors of magnetic field that we can build. And you need that because the magnetic field from your brain is tiny, it's really tiny. These, for a very long time, these were the only sensors you could use to detect those fields. But unfortunately, we don't have room temperature superconductors. Some of you will know that it's a big challenge in physics to try to get superconductivity, which is crucial for these sensors, to happen at room temperature. We don't have them. So instead, we put these sensors inside a fridge that cools them down to a very low temperature, and then we design the fridge so that it has this isn't a hole in the fridge, but all these sensors are sitting just inside the fridge, and we're trying to get them as close to your head as possible to get as precise an image as possible within the fridge. But there are many problems with this. The first problem, and probably the most significant one, is that those fridges are really expensive and complex and sophisticated. For that reason, there are only 100 MEG machines, clinical MEG machines in the world. There's one in Australia, in Melbourne. So if you need an MEG image from here, you will fly however many thousand kilometers it is to Melbourne for that. And then there are other issues, particularly around the fact that the sensors aren't right against your skull, and therefore their resolution is limited. Spatial resolution is limited to the size of about a golf ball. And if I had epilepsy, I'd really like that imaging machine to be more precise than the size of a golf ball. So what's exciting is that over the last 10 years or so, people have started to develop quantum magnetometers, sensors that measure your brain's magnetic field, that don't require the refrigerator, that don't require cryogenics. Here are two examples of companies that do this. This is Fieldline, based in Colorado in the US, and this is Circa, based in the UK. This is already starting to change the way we image the brain. And it's not just about reducing the cost and making the machines easy to use. If you have If you have to design a very expensive machine, you're probably not going to fit it out so kids can use it, because it's designed around a standard head size. These ones, much cheaper, so you can do measurements with children. Because you don't have an enormous fridge, you can do measurements on people moving and understanding how the brain interacts with your body is really fundamental to psychology, so it will to neuroscience. So it will change. Which way do I go? That way. So this is going to change not just our ability to precisely detect and characterize brain diseases, but it's going to change our understanding of the brain. In Cubic, we're working with the Australian Institute of Sport and with the Queensland Brain Institute and others to start to apply these quantum brain imaging technologies into other diseases beyond epilepsy, and particularly into concussion. So concussion is strongly connected to brain diseases later in life, and as I'm sure everyone here is aware, is connected to contact sports. Currently, if you get a concussion, the diagnosis is roughly, follow my finger, count to 10, say something, all right, you're good to go back on the field, or you better sit it out, right? It turns out it's unsurprising, in fact, that there are brain signals that you can detect with MEG that allow you to more quantitatively diagnose concussion. Why do we not do it now? A big part of it is that you need to fly to Melbourne, and it's not really practical. So we're building MEG systems that you'll be able to take onto a field and image the brain on the field. With that, I will close, maybe a few minutes early, and say thanks and look forward to your questions.
Thank you, Warwick. That was fantastic. And I can't wait to try the EEG helmet just around campus sometime.
You're more than welcome.
When are we expecting that tech? Is that in the mix soon, or?
We expect to have the helmet built within a year.
Cool.
And start to test it within a year. And the idea is to be testing on athletes within 2 years.
Wow, fantastic. Okay. Everyone, if you have questions, please join us. There's the QR code. We've had a bunch come through already, so let's get cracking. We've got some time for questions. I had a great question come in early from Nate, saying, do you see quantum computers replacing all existing computers, and if so, when?
Yeah, that's an excellent question, and the answer is no, I don't see that ever happening. And the reason is that quantum computers, there are only certain problems that quantum computers can help you with. And those are problems that have this characteristic exponential scaling and complexity. Most of the things you do on a regular computer don't become exponentially more difficult to do as you make the problem size larger. Only some of them do. So understanding a molecule is exponentially complex. Some problems in transport networks or in finance are. And so what I think you'll see is large scale, like warehouse-sized quantum computers dedicated to specific problems to begin with, and the types of problems will broaden out, the power of the computer will increase, and then they will be incorporated with high-performance computing. And over time, they'll be more and more incorporated into computing, but you'll always have conventional computers for most parts of the computation, and quantum computers just for some of the really hard parts.
Okay. And in terms of, there's a couple of questions here about monetization. Folks in the finance industry ploughing money into quantum computing at the moment, or is it mostly public funding? You know, what's that picture look like, and what do you think it will look like?
Yeah, it's a mix. There's a lot of funding from venture capital and substantial funding from governments and substantial funding from big technology companies, Amazon and IBM and Microsoft. And I would say it's fairly well balanced between the three of them. They're all investing billions of dollars. I think there's definitely a place for public money, but what has been happening is a shift towards more and more funding from industry and VCs, and that's, I think, right, because as the technology gets closer to real-world applications, you should expect industry to take over.
Okay. We've got a question here from Claire. You spoke about Brisbane's new upcoming quantum computer. So this might be a bit of a question around public funding as well and the public interest. How will you and your centre be involved with the project moving forward? What excites you about this milestone?
That's a really good question, and there are many things that excite me about it. And so I'm just trying to think which I should start with. How will we be involved?
What are your top three? What are your top three?
Okay, so let me start with how QBIC will be involved. So we have, with PsiQuantum, the state government, Griffith University, UQ, and CSIRO have launched, 2 weeks ago, launched the Queensland Quantum Decarbonisation Alliance, which is an alliance of 27 industry and academic partners to apply quantum technologies into helping us reach net zero. And that is QBIC's first big collaboration with PsiQuantum. Things like, how do you design materials for carbon capture? Those materials, so how do you need these really absorbing materials that can grab carbon dioxide out of smoke flumes. And those materials are very hard to design. So how do you design them? How do you design catalysts to better convert water into hydrogen for hydrogen energy? How do you better develop battery chemistries with better energy density, or even just better longevity of batteries? All sorts of questions like that we'll be starting to answer with PsiQuantum. A big thing I'm excited about is the technology ecosystem in Australia and in Brisbane and our state. I think that it's very important that Australia finds a way to take our great science into technology and a technology industry. At some point, we need to move from a sort of minerals-based economy to a knowledge-based economy. And I think this big concentration of quantum expertise in PsiQuantum, in other companies in Brisbane, and in universities will help us do that in the space of quantum.
Fantastic. And you'll see Brisbane as the headquarters in Australia of this movement, do you think? Are we ahead of the game?
Well, I think it's definitely true that Brisbane will have the biggest single quantum company presence in Australia. And it's also true that Brisbane has very strong heritage in quantum technologies from the very start, with professors such as Gerald Milburn coming up with some of the first quantum gates that you use to build quantum computers, and then throughout the 30 years that have gone since then. So we're definitely a leader nationally, but there's a lot of strength elsewhere in the country, and I think I think that's actually what makes Australia attractive for quantum, is that we really have a great national strength.
Is QBIC based in other cities as well?
QBIC has 5.
So you can't say Brisbane's
nodes.
the best. I'm just trying to work it out.
No, I'm trying to learn how to be a politician.
Be very diplomatic. Well done. You're doing very well. We've got a few questions about superposition. So the idea that you can have particles that are in multiple places at once with quantum technology.
Yeah.
Let's say you're explaining that concept to kids in a classroom. How do you go about it, or is it a bit
I just tried
above and beyond? Okay. Because I totally understand what it is. completely.
The fundamental problem is this: we live in a macroscopic world. As humans, we have evolved to live and understand that world. It shouldn't be a surprise to us that when you look at the world at a level of detail a billion times smaller, that things behave differently and that we can't understand it. The reality is, quantum physicists like to believe we understand quantum mechanics, but we just learn the rules and we apply it enough to the point that we kind of, it's not surprising to us anymore. But, yeah.
And you try and convince large groups of people in a room that you know what you're talking about. And you get away with it too. You're very good at that. So one question that's a bit technical that I think of as someone who sits staring way too long in front of a computer all day. For quantum computers, how do you provide the input and what do you receive as the output? What comes out the other end?
It's actually a very good question, and it's quite subtle. So obviously, I talked about this number, 10 to the power of 30. Obviously, I can't have to put 10 to the power of 30 things into the computer or else, forget it. That's never going to work. And that's actually part of the challenge. You need to find problems which are naturally suited to quantum computers not even close to every problem is suited to them. So if I think about the case of a molecule, you might start it in a kind of simple state where you only input a few numbers and let it evolve by itself. And as it evolves by itself, it will naturally incorporate this larger complexity in it. Then how do you read it out? Mm-hmm. Well, that's also really hard because it turns out that this quantum superposition, eventually you have to ask that qubit, okay, so what are you actually? Are you a 0 or are you a 1? And it has to decide, right? And it's going to decide randomly. Maybe there's a 25% chance it's a 0 and a 75% chance it's a 1 or whatever, but it's going to decide one or the other. And so I'm going to get outputs on my computer which is stochastic, which is somewhat random. And how do I deal with that? So you need to figure out how to deal with it. And that generally means running the computation many times and then averaging the results. And it turns out even when you do that, you get speed advantages in principle over conventional computers.
Does that mean error is just a fundamental part of the computing process itself? Is it more prone to error than existing computing is?
Well,
or have I opened up a total can?
No, I mean, what you say is right. So quantum computers are more prone to errors than conventional computers, but it's not really because of the measurement process at the end. It's because of stuff that's going on inside the computer. So in a regular computer, error correction is really easy, right? If I want to do it, I just make sure I've got some redundancy. Instead of encoding information on 1 bit, I encode it on 3, and then they should all be, say, 1s. I check them. If one of them's a 0, I got an error. I'm going to flip that to a 1. And so I can correct at least single errors. If I had 2 errors, I'm going to make a mistake, but then I could have more sophisticated error correction to deal with that. In a quantum computer, I'm not allowed to look at the bits like that, because when I look at them, I force them to make a decision. They're actually never a 0 or a 1. There's something in between. Sure. So even figuring out how to correct errors is really hard, and for a long time no one really thought it was possible. And there's a breakthrough in the 90s that showed you could actually do, 90s or maybe early 2000s, that showed you could indeed actually do error correction on quantum computers. And the big challenge from then, one of the biggest challenges from then till now, has been to make that work in practice. In the last 4 months, there have been several experiments that have demonstrated that you can do quantum error correction in a way that's useful on a quantum computer, which is really quite groundbreaking and critical to scaling up to large numbers of gates.
Okay, fantastic. I'll finish on a couple of really quick ones. Was there anything real in the Marvel movies in terms of quantum based on real science? Yes or no?
Yes, I know. That's a bit hard. I'm trying to, look, I really enjoyed those movies. You're thinking about Quantum Mania, is that what it was? Ant-Man, Quantum Mania?
Yeah, there was a couple.
I really enjoyed the movies. There was very little with any basis in reality in them, but that's okay.
Dashing our hopes of time travel. Okay, and in the future, will quantum compute... So we're in the middle of a potential financial crisis this week. In the future, will quantum computing affect securities such as banks or crypto? Will we have to watch out for that?
Yeah, so I didn't dwell on it in my presentation, but actually one of the reasons that quantum computing got a lot of investment early on was that the first useful algorithm for quantum computers was useful, I'm going to say in quotation marks, was one that allowed you to break RSA encryption. So RSA encryption is the encryption you use when you log on to your bank to check your bank balances. Quantum computers, that's based on the complexity of a certain mathematical problem. And it turns out for quantum computers, that problem is really easy, right? And so security agencies and governments were very interested in being the first to be able to break RSA encryption, so they invest a lot of money into quantum computers. So you should be worried. You maybe should have been worried, but the good news is that there are now post-quantum cryptography schemes that are being built in to all communication systems so that you can flick a switch and not be, at least as far as we know, vulnerable to quantum computers.
Okay. So everyone, there's an ATM just down the street here. Make an orderly queue, and please give it up for Professor Warwick Bowen. Please join us to have a bite outside, and we'll see you at next month's BrisScience, which is all about precision medicine. Thanks, everyone.